Hi. So today I'm talking about the summary of active thermography. Thermography means that we observe the surface temperature based on its IR radiation using IR camera and it can be divided into two types: passive thermography and active thermography. Passive thermography means that we observe the temperatures of the surface in ambient condition. Active thermography, on the other hand, uses an external stimulus to generate thermal response on the sample surface, and by using this sample surface over time to obtain the thermal property, depth of defect, or total thickness of the sample. It can be divided into post thermography (PT), post phase thermography (PPT), LT, Lock-in thermography, and frequency modulated thermal wave imaging (FMTWI). The idea of PT is this: so it is simple and fast. What it does is it uses a high power IR lamp to generate a short thermal pulse onto a sample. The flash duration is usually several microseconds to several hundred microseconds, and the total energy ejected is about several hundred joule to 1,000 joule. It can be used to study one stratum system and two multi-stratum system. Stratum here refers to the idea of the sample having of a plane of material that has the same thermal property, which means something like this. If we see the two-stratum system, now this is one stratum because it has its own thermal property, and this stratum has a distinct thermal property, which means it makes up two-stratum system. Well, here if we have a defect, then the sample the thickness of the defect AO should be the stratum thickness because the defect has a different thermal property, and the region without defect will have a total thickness of LR. Now let's talk about the assumption let's talk about the method for one stratum system. And there are two assumptions. The first assumption is that we assume that the defect is made of air and has much lower thermal conductivity than that of the sample itself. So we can consider the defect is an insulation to the sample, which means that when heat penetrates into the sample and reaches the defect will prevent the heat from going deeper into the sample, creating a temperature contrast over time with the region of defect and without defect. By using this characteristic, we can study the depth of defect or the thermal property of the sample, mostly using these two methods: characteristic time method and least square error fitting method. The characteristic time method utilizes the peak of second derivative of surface temperature change over time in log scale to obtain depth of defect or total thickness or depth of defect. Let's see this. So this is a figure. The solid line is surface temperature over in log scale, and the time. This is in log time, and this dashed line is the first derivative of surface temperature in log scale, and this is a second derivative in log scale. We should notice this. This is a small peak near the near equilibrium. This means that, and this peak is called T2. T2 the T2. So the definite and its equation is here, which means that if we know the thermal diffusivity of the sample, we can know the depth of the defect. But this method has a problem. First of all, it assumes that based on the mass model it uses, it assumes that the energy is absorbed at the surface and the flash is instantaneous. But in reality, this may be not the case because first of all, flash cannot be instantaneous. And secondly, we are studying SS304L powder, and the energy is very likely to penetrate into the powder and can create error in this measurement. So in order to solve this problem, we are going to use another method, least square error fitting method. It is something like this. We are going to use optimization technique to find the analytical solution based on the wanted model to have the least square error with the experimental data. So this is least square error, LLSE, and this summation means that it is because the IR camera cannot get a continuous line of the experimental data, so it is a discrete temperature at discrete time. Tx is experimental temperature data, and TAN is analytical solution based on the wanted model. Due to the flexibility of PDE, this method involves much more factors than characteristic time method. And let's have a look. So first of all, this is the simplest PDE system, PDE. So T is temperature, K is thermal conductivity, alpha is thermal diffusivity, L is total cyclus, and X is a spatial variation. The rank function is an instantaneous pulse function, and Q is the magnitude of the flash, and the bottom is insulated. Now, to obtain the cyclus of the defect, we also need to know alpha and vice versa. Now let's see what can we do to the PDE system. I add a free term. This free term expresses the penetration depth and the flash duration, which means that we can add and then we can add much more factors if we want, such as maybe we can add convection or like some other reflection from the environment. But this method has a problem because there's something like this. Because we are studying samples that has very low thermal conductivity. Like even if air is beneath the sample, we cannot consider the sample as totally insulated. To solve this problem, we have to expand our PDE into PDE system. Two strata system is needed for this lab work. And in our lab, what we use is that we use a measuring plate that is made of PLA plastic, and we deposit powder on it. The thermal property of the PLA plastic is lower using other method, and this square error method is used again. So now, again, let's say the general PDE for this. We have the subtitle means the one means the top stratum, two means the bottom stratum. Now, to know the thermal property of one stratum, we need to know the thermal property of another stratum, and the cyclus of the two stratum. And once again, we can create more complex model such as convection and thermal contact resistance. But this method still has a problem. First of all, let's see here. The surface temperature, it requires the initial temperature to be the same. The second problem is that this is 1D model, so we assume that the heating is uniform along the surface. And another problem is that the sample may have a variation in emissivity on the sample surface, although it has this value. This creates problems because, first of all, if we want to test the sample multiple times using PT, we have to wait for a long time before the sample cools down. And in my experience, usually 20 minutes. And also the flash is not instant, is not uniform. And also we don't. So in order to solve this problem, we're going to use another method, post phase thermography, PPT. The basic foundation of PPT is that any continuous lines can be expressed by a combination of vectors in vector space. And this vector in here is Fourier theory. Because what our camera get is discrete data, so we are going to use fast Fourier transform to obtain the result. What we get is a range of frequency component that has its own phase delay and amplitude. Let's see this figure. So basically what it does is studies the phase component of 1 pixel of the IR video. And using FFT, we get amplitude for different frequency and phase for different frequency. We're not going to use amplitude here because amplitude has the same problem as PT. But phase delay is insensitive to non-uniform heating, emissivity variation, and also initial temperature distribution. Basically, what it means that, and also there's another concept here, means that a thermal wave with a certain frequency is able to probe into 1.8 mu or to 2 mu of the depth. Mu means diffusivity length. It is a function of thermal diffusivity and frequency. Based on this concept, we are going to use two methods. First of all, blind frequency method. The definition of blind frequency based on this figure. On the negative axis is phase delay under different frequency. This phi s is phase delay of the sun region. Phi 2 is the phase delay with defect of Z2, and phi 1 is phase delay of a shallower defect. These three figures can create two contract phase under different frequencies, and the frequency where phase delay goes to 0 is called blind frequency. And use the concept of diffusion cyclus, we are going to retrieve the depth of defect using this equation. C1 for PPT is 1.8. T2 depends on the equipment. This is a correction constant. So the idea is, one benefit of PBT is this, because what we do is we study a range of defect, a range of frequency. This means that we have different diffusivity cycles, diffusivity lengths in the information, which means that we can observe defects in different depths in one flash. This is because, say something like this: we have a fixed frequency here. Now we have a defect right here, and this defect is definitely deeper than 2 mu, which means that the ruler we have is not long enough to reach the defect. Or if we have a defect right here, the defect is too small for the ruler to really accurately tell where the defect. But by using FFT, we have a series of different rulers to study that is able to study different defects in different depths. And another method is inflection method. Inflection method uses a peak point to study that is a function of alpha and f and frequency. Basically, it's like characteristic time method. But to this point, we still have problems for PT and PBT. That is, say something like this: if we want to flash a sample that has very low thermal conductivity, but we want to study the condition of very deep defect, what should we do? Then we really need to have a lamp with very high power to flash the sample. This is expensive and not realistic. So to solve this problem, we're going to so are we able to find a method that use lamp with relatively low power and flash the sample for a long time but still get what we want? The method is lock-in thermography. Lock-in thermography uses a lamp with relatively low power and emit sinusoidal wave with fixed frequency to the sample. And then if we now if we use phase analysis, it is insensitive to initial temperature distribution, non-uniform heating, and variation in emissivity on the sample surface. Basically, the benefit of PBT. The key principle is this: so as long as when the wave propagates in the sample and reaches the defect, it will reflect back a thermal wave. This thermal wave is weakened and its phase is delayed. But the surface of the surface temperature is still sinusoidal because it is dictated by the external stimulus. In this case, the two waves will interfere with each other, creating a phase delay of the surface temperature. And this phase delay is a function of thermal diffusivity and frequency. And again, we use the same concept of diffusion length and the equation, and we can retrieve the depth of the defect. But this method has a problem because it only has one frequency, which means that it has only one diffusion length. So that we can really only one as I said just now, one diffusion cyclist can only test different limited regions. So we need to flash the sample multiple times to observe defects in different depths. And this is time consuming because LT is already flashing the sample for longer time than ALT, and we still need to flash it multiple times. So we have to solve this problem by creating frequency modulated thermal wave imaging, FMTWI. It has the advantage of LT and PBT and remove their disadvantages. The basic principle is to emit thermal signal that has a changed frequency over time. Now let's see this figure. This figure shows a sinusoidal wave that is gradually increasing its frequency, which is called upchirp FMTWI thermal stimulus. It also has a digital version by replacing the sinusoidal wave into square wave. The benefit of having this digital version is because the average energy magnitude of square wave is higher than sinusoidal wave. Basically, it means that we can stimulate the sample more using under the same power lamp. And once again, since we are having information under different frequencies, we are going to use FFT to observe different defects in different depths in one flash. Now let's look at the example. This is a 30-layer CFPR sample with one defect in every 2 layers. And the bigger the number, the deeper the defect. As you can see here, we are using phase analysis to study the IR camera under different frequency. As you can see that we can directly see all the figure using one flash. So basically, this solves all the problem as I mentioned in the past. And this is all about what I have to say. And this is my reference. Do you have any questions? Thank you.